Hello everyone, welcome to the mechanical vibrations tutorial. Today we are going to continue on the vibration under non-periodic force. So let's begin. So as you may remember from the previous tutorial, we discussed the case that the force applied to the system is not periodic and it's not harmonic. For example, if we have a mass spring damper system like this that we have shown before, like M, K and C, and there is a force Ft applied to the system. So if this force Ft was harmonic or periodic, we showed how to find the response of the system, and we also showed the case that Ft is not periodic, like there is no repetitivity in the the shape, or there is no frequency associated with Ft. For example, if we showed the case that Ft applied to the system has an increasing behavior, or there might be a exponential decay and so on. So these are the cases that could appear in the system, and we show how to find the response of the system based on the convolution integral. So we show that for these types of cases, the response of the system, or say for example xt, is equal to, well, there is a component that we need to calculate for the integral, is equal to basically 1 over m omega d from 0 to t, and t is the upper bound, which appears in our final response and makes it as a function of t, f tau, and tau is basically the variable of integral, e minus zeta omega n t minus tau, and sine omega d t minus tau d tau. So basically we need to find this integral and calculate that, and we need to plug in f tau here. So we know the function of ft, we can simply plug it into this integral and find the response of the system. So for the undamped system, so let's say for undamped system, it's even easier because there is no omega d or zeta, and then xt would be basically 1 over m omega n, the integral from 0 to t f tau sine omega n t minus tau d tau, right? So it's even easier to find this integral. So we remember that, but for the cases that ft we have it as an explicit function of time, we can simply solve for this integral, right? However, there are cases that the force F is not continuously existing with time. This is a very important case that I wanted to assign this tutorial to. So basically imagine that Ft is not fully existing in the system. After a certain time the force disappears, and which is even a very practical case in vibration system. So imagine that, for example, if this is Ft and this is time, after a period of time, or after a certain amount of time, the force disappears. So for example, maybe I should write it again. So basically this one is Ft, right? So imagine the force, say for example there is a constant force, and then after a time, say for example, I don't know, t naught, the force stops. Or there is another case that, for example, we have this Ft and there is a downward ramp like this, and after t naught the force disappears. Or I can give you so many different examples, like an increasing one, or maybe this increase is not necessarily linear, like this one, right? Or like something like this. Or in other cases it could be a combination of them, like for example you have an increasing and then decreasing force. This is also one case that you can see, say for example at t naught and t1. So this is t and this one is ft, right? So these are the cases that the force could be pretty much like a piecewise function. So it means that the force exists, or there is a function of force in some time ranges, and then it disappears. So we basically have piecewise expressions for the force Ft, and we need to know how to deal with the system. So before we basically continue. I just want to say that we can that component of the integral, say for example the xt, we define it equal to m omega d 0 to t f tau e minus zeta omega n t minus tau sine omega n t minus tau d tau. So this component of the integral, basically, if you may remember that from before, we can call it basically g t minus tau. So in fact, gt is just basically there is no t minus tau, only t, right? So keep that in mind. We can call this part as g t minus tau, or for example, the response of the system, we can simply say that xt, for the general case that the force is always existing with time, we can say that it is equal to 1 over m omega d 0 to t ft and g t minus tau. The reason I'm repeating it in here is I just want to tell you what gt minus tau is, right? Just keep it in mind. And for sure, for the undamped system, gt minus tau is simpler, right? Okay, now I just want to go back to the case that we are discussing today, when the force disappears, or the force has different functions at different time ranges and then disappears or just go away. So for example, say for example any random function, say for example there is a function of f to a certain time and we call it t naught, and then the force disappears. So how can we find the response of the system for these cases? So in fact, for these cases, I'm gonna call it like the function for here f1 t, right? And after that it is 0, right? So how can we write the function for this thing, for this force basically? So ft is equal to f1 t from 0 t to t naught, right? And for values greater than t naught, it's equal to 0, right? So for t greater than t naught, right? So this is the function for that case. And say another example, for example, this is t and this is ft. Say for example we have one function here and then we have another function here and then the system stops here. So we have basically it's t naught and t1. So we have f1 here and then we have f2 here, right? So how can we represent ft would be equal to f1t and f2t and 0, right? So for 0 t to t naught, for t naught t to t1, right? And for t greater than t1. Makes sense. So how can we find the response for these cases? We have to break the response for each time range, and we have to find the response for each one separately. So in fact, the response or the expression of the response will be different in each time range. For example, if we have, say for example, ft equal to f1t for 0 t to t1 or t naught and 0 and t greater than t naught. For this case, we can say for t between 0 and t1, so we have or let me just write it t naught. So basically I go back to tools. So we have for 0 to t naught, the response of the system will be found through our regular integration. So x of t would be 1 over m omega d 0 to t f, and here basically we have f1, so we have f1 tau g t minus tau d tau, right? And so whatever we find through this integral is only valid for this time range. However, for t greater than basically t naught, we have to do this way. So xt would be from 1 m omega d, and we can use a square bracket, from 0 to t naught f1 tau g t minus tau d tau, plus from t naught to t 0 times g t minus tau d tau. So as you can see here, the second component, which has 0 times gt or gt minus tau, is basically 0, right? So basically this part, or let me actually close the bracket here, right? So what we get here is, so this component would be 0, so which makes it easier, right? So for this case, xt would be 1 over m omega d, 0, only 0 to t naught f1 tau g t minus tau d tau. That's it. So as you see, we have two different integrals. The first one, we have this upper bound and lower bound. This one is 0 to t naught. And basically the integration would be easy. Sometimes it's similar. You just have to, use a different boundary or upper bound for the integration, right? So we want to do it do this method for this example, and but before just doing that, I just want to say, if we have, say for example, another component, say for example we have I want to write it with different colors. So if we have, say for example, f2 from 0, not 0, like t0 to t1, and then we have 0 for t greater than t1, we have 3 integration, or we have 3 parts. So this one, right, and that one, and the final one. So for the first one, we integrate from 0 to t f1 g t minus tau dt d tau. This for the second one is from 0 to t naught, whatever, like f1 g, and plus the integral from t naught to t f2 g d tau, and the last one is only from 0 to t naught plus t naught to t1, right? Because the rest would be 0. So we can apply this procedure when we have more components, right? Or like the piecewise function has more functions or more time ranges with different forces, okay? So let's do this example to see how this method works. So in fact, in this case, we have an undamped system, which makes it even simpler, and so there is no damping in the system. We want to find expressions. As you see, it says expressions, which means that we have two responses for different time ranges. So this is the force applied to the system, increases from 0 to f naught during this time period, and after that it is 0. So there is no continuous function which we can simply which we could have simply apply the integration. We need to break it into different times, right, or different time ranges. So for this case, f tau, if I write it here again, it's a piecewise function. For the first part is f naught tau over t naught. It's just a linear. You can find the slope and simply find the function. For basically it's f tau, right? I just wrote it f tau, but you can simply write it ft. Or let's why don't we write it ft here? So this is ft. So for t from 0 to t naught, and then 0 at t greater than t naught. So this implies that we need to find the responses or expressions twice, or find the integral twice. Once for 0 t to t naught, and then for 0, or not 0, for basically t greater than t naught. So we have two separate parts or separate expressions for this response. Each response is only valid for the assigned time range. Okay, So let's do that. Basically, let's do the integration, and I'm sure you already know how to do these types of integrals, and you need to basically review like your math courses or calculus for integration. So let's say for t between 0 to t naught, what we have here, xt would be equal to 1 over m omega n here from 0 to t, right? Because t is varying from 0 to t naught. It's equal to f1 tau, right, sine omega n t minus tau d tau, right, which gives us xt equal to 1 over m omega n. What was f1? F or f naught tau divided by t naught sine omega n t minus tau d tau. So the rest is just integration. We can take the constant components this out, and we have xt equal to f naught divided by m omega n t naught from 0 to t tau sine omega n t minus tau d tau. So to find this integral, we can use different approaches, but the simplest case is to define a new variable, like set t minus tau equal to u, and then basically then you need to do the integration by part. Basically you need to find d tau and du, and then you do integration by part. I really basically don't want to go through the integration because we have done that before. So what we got for this part, I just want to show it in here, and I just want to tell you that for basically t between 0 to t naught, so only in this range, our xt after we find the integral, xt would be equal to, I just want to basically show the final integral. The answer for the integral is equal to f naught over m omega n t naught. The integral is 1 over omega n squared sine omega n t minus tau minus basically, if I go down, t minus tau divided by omega n cos omega n t minus tau, and the whole thing varies from 0 to t, right, for tau. And you can double check my integration and make sure if I found it correctly, or you can find it yourself basically. So it doesn't matter, we just want to know how to apply this method. So for this range, if we apply the upper bound and lower bound in tau, so basically we need to apply t and 0 into tau. So this is for tau and this is for tau, right? So like how you apply the upper bound and lower bound, and make sure that the variable in the integral and this function is tau. So the final response for this period or this time range would be f naught divided by k t naught times t minus 1 over omega n sine omega n t. That's it. And you may be asking why this case here, m omega n and k are somehow related to each other. But that's not the end of the story. So far we found the response for the first time, basically domain. Now we have to find it for another one, or basically for the case that we have t greater than t naught. So for t greater than t naught, we have another expression. In fact, our response would be different. Now we just write it like this: xt is equal to 1 over m omega n times the integral, the first part of the piecewise function, 0 to t naught f1 tau sine omega n t minus tau d tau, plus from t naught to t 0, or the second component of the piecewise function, sine omega n t minus tau d tau. In fact, you don't have to write the second part because you already know it's gonna be 0. The only reason that I'm writing is to know why we have t naught here instead of t, right? And we have 0. So this part is 0, and then xt would only be 1 over m omega n from 0 to t naught, and we already know f1 is f naught tau divided by t naught sine omega n t minus tau d tau. So as you see, it's similar to the previous case, the integration. The only difference is the upper bound and the lower bound, right? Here we have 0 and t naught, so we know the answer of the integral. We just need to plug in 0 and t naught into tau instead. But when we have more components or more functions in the the piecewise function, then we don't have a similar integral necessarily, or maybe we have similar integral but with more additional terms, right? So now we know what to find. It's pretty simple. Basically, for t greater than t naught, we have x t equal to f naught over m omega n t naught from 0 to t naught here, and then we have only tau, right, sine omega n t minus tau d tau. Again, you can find the integral, pretty simple. Just you can use u equal to t minus tau and then find du, and then you have to apply the integration by part. We did similar things before and I don't want to spend time on it, and then I just write down the final answer for the integral when we apply 0 and t naught into our boundary, upper bound and lower bound, which gives us f naught k and t naught times 1 over omega n sine t minus t naught. See, now t naught appears in our response or in our components, plus t naught cos omega n t minus t naught, and you see the t is existing as expected, which means that our response is a function of time. Okay, minus 1 over omega n sine omega n t, right? So we found the response of the system, and if you compare this expression with the previous case or for the previous time range, you would see that they are totally different. So which means that when we apply such force to the system, the response of the system at this period would be different from the rest of the time, right? And you have to find them separately and apply. Like imagine you want to get one amplitude at one point, you need to use the right expression depending on the time that you are looking into. Okay, and again, don't forget that when we have and I want to repeat that again, when we have multiple components into our piecewise function, say for example we have a function like this and we have f1 and f2 and then 0, so we have, say for example sorry, it's not 0, it's t1, and then we have t naught, and our f t would have f1, f2 and 0 from 0 to t1, and or t naught, basically from t naught to t1, and for t greater than let me just write again, either one would work, so I would use this one. Yeah, so this or you don't actually need that, or we can use this one anyways. And we have t greater than t1. So let me just make it clear. Anyway, so what I want to say is that in that case we need to calculate 3 times. So first we calculate for t between 0 and t naught, then for t between t naught and t1, and for t greater than t1. So for this one we have like whatever, like we can say xt equal to 1 over m omega d, and then we have a like an integral from 0 to t, and we only use f1 tau g t minus tau d tau. For this case, xt has 2 components, 1 over m omega d from 0 to t naught f1, and then like g t minus tau whatever, plus t naught to t f2 g and whatever. And finally for this one we have 3 components basically, or the last one would be 0, so we have only 2 components, from 0 to t naught f1 g, and plus, you know, t naught to t1 f2 g, and we have a, you know, t1 to t0 g, which we don't calculate it, right? So this is how this method works for multiple piecewise components in the piecewise function. So I hope you got the idea of how to apply this procedure for the cases that the force function is not continuously continuing basically with time, and this procedure is very important because in many cases the force does not exist like forever. Okay, so I hope you enjoyed this video, and stay tuned for the next videos.